Happy Tuesday. I'm sorry that it's a very snowy day, and at the moment none of you are here, so I'm talking to an empty room. But I'm going to carry on as if you were here. Ah, here's somebody. Good. Um, we were talking on Thursday about our asset and liability stream. We had the example of having to pay off two one value liabilities at time one and time two, and then we were looking at how we could match the assets to that. And the issue was that if we didn't have an exact match where we were paying off exactly one at time one with an income of one at time one and exactly at time two with an income of one at time two, then we were looking at the possibility of what could happen in a rate change. So that was this setting from Thursday. So if there's a rate change suddenly, I could find myself in a deficit. If our interest rate changes from whatever we originally set it up at when we were calculating all of our assets and liabilities to something else, then we could find that the present value of our assets under this new interest rate is less than the present value of our liabilities under this new interest rate. And that's a deficit position. I don't like this idea. I really would prefer not to have a deficit. I'd prefer to be able to say I'm covered at all times. But that idea of being covered is really recent. In 1952, F.M. Reddington came up with the idea of immunization for a cash flow. And in this case, we're using cash flow as the generalized idea of assets and liabilities coming in and out. If I can structure the assets carefully, in this case, with respect to the liabilities, then for small perturbations in the interest rates, I can always have the present value of the assets be larger than or equal to the present value of the liabilities. I'll never fall into a deficit position. But the real question is, how the hell do I manage this? What is this careful structuring of assets? I want to use this equation here, equation 7.9, as my basic position. So I'm going to start with the idea that I've balanced everything at time zero. So I'm using that rate, I naught, whatever it is, this nominal interest rate that I'm going to start with. And I'm going to say, okay, I have my assets and my liabilities are matched at time zero. This is that equation 7.9. So this is my hopeful starting point. There is a balanced position. Then I want to say that I'm going to look at this from a calculus lens. All right, what the hell does this mean in calculus terms? That first equation, 7.9, says to me that my assets and liabilities have the same present value. This second equation says that if the interest rates change, the value of the assets and the value of the liabilities change the same. My change in interest for assets and liabilities, when I look at the particular interest we are looking at, they have the same first derivative. So this says they have the same first value. This says they have the same first derivative. If I can look at the second derivative, and compare those, and my asset second derivative is bigger than my liability second derivative. Okay, wait a minute. What does that mean visually in terms of the two functions? If the asset liability has a larger positive concavity, means it's concave up, it's more concave up than the liability one. And if it's concave down, it means it's less concave down than the liability one. So the liability one is under the asset curve. Not just at that point, but in a little interval around it. Both in straight line, they have the same first derivative, but then they have different curvatures. And the asset one is always on top. So these three equations together, I claim give me enough. Let's think about the function based on interest rate. Present value minus of assets minus present value of liabilities. According to the first one, 7.9, h of I is 0. According to the second equation, h prime of I is also 0. And h double prime of I is positive. Wait a minute. I've got a function whose y value is 0, whose slope is 0, that's concave up, right? I must have a minimum there. These are all at I0. Well, look at the picture we've drawn. If I think of some small interval around I0, the entire graph of h of I must be positive there. This doesn't have to be a huge interval, but in a small interval around I0, that's always positive. And if it's always positive, that means that the present value of my assets must always be greater than the present value of my liabilities in that section. In other words, if interest rates change, whether they go up or down in this picture, I don't care whether they go up or down. I can't ever do worse than I'm doing right now. There's some interval, IL to IH, low to high, around I0, where h of I, that should be bigger than or equal to 0. And that means that the present value of my assets is bigger than the present value of my liabilities. Which means I cannot hit a deficit. I'm immunized. I'm immune from a deficit position, provided I have these conditions on my cash flows so that I have the same value today. I have the same first derivative today. And the difference in my second derivatives is in the favor of the assets. Reddington proved this a little more rigorously than I just did, wrote this up in a paper, and people liked it so much they named it after him. And he said, if my assets satisfy those three conditions, I'm immunized against small perturbations in the interest rate causing a deficit. So, page 345, we have the definition for Reddington immunization. They have the same present value. They have the same first derivative. The following is a typo in the textbook. I want this to be a greater than symbol. The textbook wrote an equal sign. That's incorrect. It should be greater than. Then the liability cash flows are Reddington immunized against change deficits due to interest rate changes by the asset cash flows. So I need all three of these conditions to be met to have my Reddington immunization. All right, wait a second. What the hell? Second derivatives measure concavity, right? Curvature. That's what we talk about in Calc 1. In Calc 3, we talk about this for multivariate functions. But in general, I'm thinking of the second derivative of a function of I in this case. And instead of thinking concave, let's think of the other side. Let's think of the convex behavior. And so we can just as easily say that this is a measure of convexity. F double prime of x in calculus we talk about concave up and concave down. But I can reverse those and think of convex. So a function that is concave up is convex down. And a function that's concave down is convex up. It's just looking at the other side. So the idea for a cash flow is to talk about convexity. And there are two versions of this. There's like a Macaulay and a modified. There's two versions of convexity. I'm going to work with modified convexity to start with, and then we'll look at the other ones subsequent to that. Modified convexity is the second derivative divided by the present value. Wait a minute, I'm taking a derivative, I'm dividing by the original. That sounds like a logarithmic derivative, but I'm dividing the second derivative, not the first. So it's not quite a logarithmic derivative. But let's consider for a moment what that looks like. Here are my asset cash flows. Then the present value looks like that. Bring each one back in time to today. Hang on a second. What's the derivative of that with respect to I? It's a series. When I take the derivative of a series, I take the derivative term by term. So I can ignore the fact that it's sum. I can just say I'm going to take the derivative of that thing with respect to I. That's the derivative in here. So this is constant thing to a power. So when I take the derivative, I get minus t 1 plus I0 to the negative t minus 1. But notice what happens when you put in, I've written k here. That should be t. What happens when you put in t equals 0?
Everything cancels.
Right, so that's a 0. So really I can do this from 1. We'll put the minus sign there, t 1 plus I0 to the negative quantity t plus 1. It's minus t minus 1, so I'll just put the minus sign outside. But that's the first derivative. What's the second derivative? I do the same thing again here, right? So I bring this down. Well, the minus signs are going to cancel. And I get the sum at t, t plus 1, 1 plus I0 to the minus t minus 2. And again, this time t goes from 1 to infinity, just like it did up here. Well, there's my modified convexity. My modified convexity at an interest rate of I0 is this expression divided by that expression. Notice that the first one got canceled out, so this now starts at 1 instead of at 0. This is for the assets. I'd have the same idea for the liabilities. And so my second derivative equation basically says that the modified convexity for the assets is bigger than the modified convexity for the liabilities. I like these expressions in terms of the discrete sums rather than writing this in derivatives. And if you look at our formula sheet, you will see in our discussion on immunization, we have present value of assets equals present value of liability. There's my sum. The first derivative should be equal. Well, that's the duration being equal. And there's TA, T, and here's T squared, T squared. I take two derivatives, T plus 1. Same idea. But notice the inequality here says that the modified convexity of the assets should be bigger than the modified convexity for the liabilities. And that's what we came up with for our equation about the second derivative. The idea of immunization really means that my assets cash flow is more spread out than my liabilities cash flow. My liabilities cash flow come at discrete intervals, and they're big in some places and small in others. My assets are more spread out to cover things. I can actually quantify that. If I have an immunized cash flow, then I look at this equation that we just wrote down about the second derivatives. A little bit of algebra shows me that my assets, when multiplied by t minus the Macaulay duration squared, what the well, that t minus Macaulay duration squared idea looks like the standard deviation idea. Remember, we take a number minus its average somehow and spread that. And the Macaulay duration is the average time in my cash flow. So what I'm really saying here is if you take the standard deviation, the variance in our cash flows for the asset has a wider variance than the liabilities. And that means I'm covered more often. All right. So the real question is, what the hell do I do with this information? How can I put this to any use at all? Because it's one thing for me to say, oh, we've got this immunized position. How do I find an immunized position? How do I know what an immunized position looks like? Well, let's go back to our example about severance packages. Okay. Example 7.5 about severance packages. Now, let's find this. We had an initial zero coupon bonds at a flat term structure of 10%. I want to buy zero coupon bonds to cover the idea that I would have liabilities of. Now I need to write out my liabilities. Okay. I need your help. We were dealing with 3 retirees, right? And one was going to be for 10 years, one was 12, and one was 15, right? And they got $100,000 when they retired at age 65, and they got 10,000 each year, right? Okay. So it was 10,000 per year until 65, then 100K at age 65 each person. So the first person was going to be 65 in 10 years. person 2 in 12 years, and person 3 in 15. So liability 1 in the first year, how much do I owe in the first year? But I owe 10,000 per person that's not 65 yet, right? Aha. And that's not only true in year 1, that's true in year 2, 3, 4, all the way up to year 9, right? What's my liability in year 10? Well, all 3 people get their 10,000 and one person gets 100,000, right? Person 1 gets 100,000 when they turn 65. 130, right? 100,000 plus the 30 I was giving to each one. But then year 11. What do I owe in year 11? And in year 12? Up, this is different again. Because I owe this person, a person 2, I get their $100,000. And then in year 13 and in year 14, but in year 15, okay. I already know that the present value of my liabilities is $300,000. We worked that out in example 7.5. I want to buy 2 zero coupon bonds to cover this. So there's my complete list of liabilities. I want my assets to total a present value of $30,000. But I'm going to buy 2 zero coupon bonds at 2 times with 2 values. Now, depending on what pieces of information I'm given, I can either know the times or the years or one of each, and I can figure out what the right setting is. But I know that the present value of these assets will be given by the present value of those bonds. That's exactly my total assets right now. That means I want these 2 numbers to be equal. To have a balanced asset portfolio, I want these 2 to be equal. But if I want to be immunized, what else do I want? What's the other thing I want? There were three things for my immunization. The first one is that they have the same present value. What's the second one? I wrote it down.
Well, the referee, the.
Okay, hang on a second. I'm going to use the series idea. The present value of my assets first derivative. I take the derivative here. That's going to be minus T1x 1.1 to the minus T1 minus 1 and minus T2y 1.10 to the negative T2 minus 1. Notice I have to multiply by the extra t in there. But with a little bit of fudging, I can use the equation that we had here. And I can say, well, really all I need is the extra t. I multiply by an extra 1.1, the minus 1's go away. And so really I can say T1x 1.1 to minus T1 plus T2y 1.1 to the minus T2. Multiplied by negative 1.1. The minus signs went away. Now I need to do the same thing for the liabilities, but there were a lot more liabilities, right? Okay. Page 347. Here is a long, unpleasant, typo-ridden calculation out of the textbook. Here, on the left is the first derivative idea for the first bonds, the assets. And here are the typos. Here are 1 through 9. They got number 10 wrong. Here's 11. They got it right, but they got 12 wrong. 10 should be 130,000 because we have to pay that one person who reached 65 their extra 100,000. 12 should be 120,000 because we have to pay that one extra person, right? So those two numbers are wrong. Please fix them in your textbook, page 347. But please notice, if I know the times or the values, I have two equations. I have the equations about the present values, and I have the equations about the first derivatives. But the stuff on the left has T1, X, T2, and Y. This stuff is all numbers. I can work out this number. So they did. The thing on the right is a number. I have this equation has a present value of 300,000. I have this equation has a present value of 2.26 million. Hang on a second. Two equations, two variables. Provided I either know the times or the values. Suppose we are told T1 is 0 and T2 is 15. Then our two equations look like this. 2.26207.23. This is the first equation about the present value. This is the equation about the first derivative. Wait a minute. Isn't that going to be a zero right there? 0 times x, that's garbage. That's this piece right here, and that's multiplied by 0, so this is 0. Which means you can solve for y right now. Give me a number. And then I can take that, put it back in. 1.1 to the 0 is equal to 1. So this is x equals 300,000 minus y times 1.1 to the negative 15, which means you can solve for x as well. $149,000. What was the rest of it?
194. 85.
Wonderful. Now, they have the same present value. They have the same first derivative. Do they satisfy the second derivative condition? Here's where I tell you up front. This calculation by hand is a pain in the ass. Okay, the second derivative is going to be t squared x 1.1 to the negative t1 plus t squared y 1.1 to the negative t2. And we said that the times were 0 and 15. This is the present value of the assets second derivative. The present value of the liabilities. Wait a minute, there were 15 different liabilities, weren't there? I got to do this. And I got to multiply each one by t squared. I am the first person to tell you right now, I'm not doing this by hand. The textbook actually wrote it out again. They wrote it out. They said, here is the second derivative for our liabilities. Notice 1/30,000 times 1.1 to the negative 1. 2 squared, 3 squared, 9 squared, 10 squared. There's my 130,000. They got it right down here. But this is the calculation for the second derivative. I didn't do any of this by hand. I cheated. Here is our liabilities for all 10 years, right? I'm sorry, all 15 years. There's their total present value. In each of these, I did liability times 1.1 to the negative t. In the second column, I did t times. And in the third column, I did t squared times. So these, that's the first value. There's my first derivative value. Here's my second derivative value, 22.7 million. Yikes. I had time 0 and time 15. Really, all I need to do is know whether or not the asset number is bigger than or smaller than that. So, with time 1 being 0 and time 2 being 15, I actually worked that out right there. There are the two numbers we got. I did this with the matrix commands, but we did it by solving the simultaneous equations. You can use matrix commands like this. You can do this on your calculator. You can do this graphically, however you want to solve the simultaneous equations. Am I immunized? There's the present value of my assets. It's bigger than the present value second derivative of my liabilities. We are immunized. In other words, if I want to cover these retirement funds and I buy 2 bonds, one for 149,194 today, and the other for 629,950 zero coupon bonds. At time 15, I have enough assets coming in throughout this entire time to be able to pay off everybody at an interest rate of 10%. And if the interest rate changes, I'm still covered. Say we are in year 2 and the interest rate goes from 10% to 9.9%. Oh no, nope, I'm immunized, I'm fine. Maybe it goes to 10.2%. I'm even happier, I'm earning more money. But if it goes to 9.8%, I'm immunized. I'm okay. Small deviations. We have not worked out how big or how small, but there are small deviations where I'm still fine. It would be nice to know how far, but I don't know that yet. Questions? The textbook also asks, what if instead of buying these at time 0 and time 15, we bought them at time 6 and time 12? I can't afford to have my 0 coupon bond come due today, so I'm going to have it come due at time 6. I'm going to have it come due at time 12. Or maybe I'm going to have one of them come due at time 2 and one of them come due at time 14. Do I still have enough money to pay everybody everything? But if I don't actually have the first bond come due until time 2, I have to borrow money today to pay the people their first $30,000 in year 1 and year 2. So I borrowed 60 grand in year 1 and year 2, and then I get that first bond payment. That 0 coupon bond comes due at time 2. So I built up some debt, but I know I have this money coming in that's going to clear that debt. As long as I can say that's true here at time 2 and time 14. Can I do this? Well, my first bond that's going to be due at time 2 is going to be $195,000 instead of $149,000. So I'm going to need more money at time 2 than I did at time 0. Because I built up some more debt, I have to pay the interest off there. And the money that comes due at time 14 has to cover whatever I built up in the interim, as well as give me enough to make those final payments. Am I immunized here? Yes. I do the same calculation. Notice that 22,709 liabilities number. That's the number we got off this set of calculations. That didn't change. But I'm immunized here. If instead of being 2 and 14, I did 6 and 12, again, I can work out my coefficients to get the first bond is going to be $395,000. At time 6, I've got to pay off $30,000 plus interest, plus have enough money to make the next payments until I get my next cash at time 12, or at least to offset the accumulated debt I will balance. And my time 12 payment's 241,700. But this time, I'm not immunized. If my rates change, I could be screwed. There's not enough leeway here in this case. On page 347, they worked out the 015 case by hand. I don't want you to do this by hand. I want you to do this here. You're welcome to take this example from our Canvas page and keep working with it. But I think in general, the idea of checking for our immunization is important. Questions? Okay. This leads me to one other definition and then a more general idea. I said there were 2 types of convexity, and I started with modified convexity. But the other one is Macaulay convexity. Which is basically the easier version of the series of cash flows A0 through AN at times t equals 0 to n at interest rate I0 is to take the second derivative and divide it by the present value. Please notice it's the present value of all but the time 0 payment, because the present value of the time 0 payment is the time 0 payment. So both of these sums start at time 1. It turns out that the Macaulay convexity is equal, the modified convexity is equal to the Macaulay convexity plus the Macaulay duration divided by 1 plus I0 squared. So Macaulay and modified work together to make my life easier. let's consider for a moment what I said about our range of interest rates. We were immunized. I'd like to know how big that range is. Back when I talked about immunization, I said there was a low rate and a high rate around I0. So it might be to my benefit to actually graph what our H of I function looks like. Because that was the picture we were dealing with. We said, hey, I've got this little bitty interval where H of I is going to be concave up, convex down, around our stated interest rate where it'll be exactly 0. And if we nudge the interest rate in either direction, we should be fine. I had 2 cases where I was immunized and 1 where I wasn't. Page 349. These are the 2 cases where I was immunized. Here's my interest rate, right here. Here's my interest rate right here. Notice that we are at 0. We have a horizontal tangent line at 0. A deficit could occur if my interest rate gets far enough away. You see how this starts to change and come back down? So these are not to scale drawings. If my interest rate moves far enough away from our point 1, we could be in deep, we could end up in a deficit position. So I'd like to know whether or not I'm immunized all the time, or if I can find that low and high end. So let me go back to those 2 pictures that we were just looking at. In the picture on the left, goes with that time 0 and time 15 bond. The picture on the right goes with the time 2 and time 14 bond. Notice here that we never duck back down to being negative. But over on the right, we do duck back down to being negative. Now, it's interestingly enough, we duck back down to being negative when I is 425%. If you get an interest rate of 425%, run like hell. I don't know what's happened in the universe that interest rates went from 10% to 425%, but that is clearly the universe has changed a lot. And not only are the assets I'm not going to worry about immunization, I'm going to worry about whether the mushroom cloud is big enough. What the hell just happened? But clearly here, I don't ever come back down to being negative. I'm fully immunized. Here, for reasonable interest rates, I'm fully immunized, but if something unreasonable happens, then I have a problem. So really, one of the things we need to look at is how far out does my Reddington immunization actually go? Now, I did graph these in Grapher on the Mac. That's actually completely illegible. So let me get the picture that I pulled up earlier. Here we go. Here is, close. Cancel the transcript. Here's the picture in the textbook for the 0 and 15 done to scale. Notice I've got interest rates going all the way on the right here to 100%. There's my 10% mark where we touch the x-axis. Here's interest rates at 100%. Again, I'm not going to really concern myself with interest rates way above 100%. That's insane. If we get to that point, civilization's in trouble. I'm fully immunized here. Notice that to the right, my first derivative is still positive. There is an asymptote there as t goes off to infinity. And if I can show that that asymptote is still positive, I'm doing the right thing. So what I really need to figure out is how to get this. Interest rates change over time. I need to update my portfolio to make sure I can stay immunized. I want to be immunized against these sorts of interest rate changes to stay solvent as a business. That's a positive behavior. I think this is an appropriate place for me to stop for today, and I will go through the example of full immunization on Thursday. That's where we'll end Chapter 7. Please note, I did change the due date for Chapter 7's homework. It is due Monday at 4 o'clock. Now, I will be in class on and off all day Monday. My actual schedule is on my door. If you want to physically hand that to me sometime on Monday, that's fine. If you want to scan it and email it to me, that's fine. If you want to slide it under my door, that's fine. I'll be back from class around 4 o'clock. I'm giving a makeup exam at that point in time, but I will pick up your homeworks and grade them as soon as I can. I also did have a question for you. You all are my last exam. Our exam is on Thursday. Normally, during the day before the exams, I would have office hours. You're the only thing I've got Thursday, so I would have most of the morning available. If you guys want me to hold office hours or open question and answer sessions about the exam, let me know. And if Thursday works, let me know about that. Otherwise, I will see you all this Thursday for our last class of the term. Holy moly, we made it. See you all then.